What's up guys, this is Walid and today's problem is the dam and plug. So we have this dam in here that D2 is 6 meters, D1 is 15 meters, and we have distance between here to here is 1.2, and they gave us the diameter of this pipe, so just make sure it's in divided by 2 and make it in meters so we can get the radius. Cool. So now the first question is, what will be the total force on the left side of the plug? So on this side right here, what will be the total force? So we know that force is equal to pressure times area. Okay, so we know area, we just need to find the pressure. So pressure will be, we know that it's open from here, so that means we need to add the atmospheric pressure. So P at ATM, atmospheric. Then we need to add the pressure from the water itself. So density of the water times G times D2, so distance from here to here. Alright, so atmospheric pressure is 101,300 plus 1000 times 9.81 times 6. Cool. Now for this guy I got 160 Pascal. And then the area is equal to, it's a circle, so it's pi r squared, and so area is equal to pi 0.025 squared, which will be equal to 0.00196. You plug in those back in here, the A and the P, you'll get force equal to 314.47 Newton. And then what's the total force on the right side of the plug? So the same thing, force is equal pressure times area. So pressure will be equal to, on this side in here, there's no water, and we know that there is atmospheric pressure. So it's 101,300, and there's no water on here. So we're going to neglect those guys, okay? And then the area is the same thing, 0.00196. So the force will be equal to 198.8 Newton. Let me make sure of this number. 101,300 times 0.0016. Yep, we get the same number. Alright, so what's the gauge pressure on the plug? Okay, gauge pressure is only P1 minus P2, and let's call this P1 and this is P2. Okay, so 160 minus 101,300, okay, which is equal to 58860, which, if you think about it, it's the same as when you do P, G, H, and H in this case is D2. Yeah, I think so, I'm pretty sure. It's the same thing if you do the values of these guys. Cool. Alright, so if the plug were to be removed, how much water would flow out in 3 hours? So let's find the velocity first, and then we'll change it to volume per cubic meter, and then we multiply by 3 hours. So let's do it conceptually first. So P ATM plus P, the density of the water, GH, is going to be equal to the atmospheric pressure plus half the density V squared. Okay, so this is coming out that this equation comes that when we cancel the atmospheric pressure, this guy and this guy is kind of like the potential energy from the water coming from here and going from here. So we're assuming that potential energy at this point is 0. And here is maximum. Okay, and here is KE is max, and here KE is 0. Okay, so now when we do the math, the densities will cancel, so that leaves us with V equals 2 times G times H, and H is just the 2 square root of that guy. Doesn't this look familiar from like physics, the mechanics one? Alright, so V is going to equal to 9.81 times 6 meters, square root of that, so V is going to be equal to 10.849 meter per second. Right now we're going to do some math to change this, so 10.849, this is meter per second, multiplied by 60 second, divided by minute, times 60 minute, divided by 1 hour, times, and they want 3 hours, times 3 hours. Alright, so this will give us the value, the velocity in meter per hour, and then we multiply it by the area. So the area is pi times 0.025 squared. Okay, so for this guy I got 230 meter cubic of water. Cool. Alright guys, hope this helped. I'll see you in the next video.